Hi, I'm Stuart Matthews, and I'm here to talk to you today about Model Code 2020, which will become the latest version of the FIB Model Code for concrete structures. In this presentation, I'm seeking to take a wider perspective on the code, and in regard to this, I should be giving an overview of selected parts of the model code and referencing supplementary information in references to technical papers which describe other facets of the code which I can't consider today. But as a starting point, I think it's important that we all recognise that all engineering and construction works are undertaken to meet an established societal need or goal. And accordingly, Model Code 2020 takes sustainability as a fundamental and overarching consideration for new existing concrete structures. And in that regard, a key aspect is sustainable decision making, adopting the widely used 3 pillars concept. So here you can see the 3 pillars: economic, environmental, social and societal aspects. And here in the sweet spot in the middle is a consideration of all of these 3 factors without any individual weighting of those considerations. And FIB Model Code 2020, with its technical content for the design of new concrete structures and adaptation, upgrading, lifecycle management of existing structures, seeks to be positioned here at the centre of the sustainable decision-making approach. Let us first consider some contemporary circumstances and concerns which are influencing Model Code 2020. I think we've all heard and recognise that there's a critical need to reduce global emissions of CO2. And of course, this situation brings implications for Model Code 2020 in terms of its conceptual scope and the nature of the technical guidance it provides. Model Code 2020 innovations and improvements aspire to assist the construction industry reduce its embodied carbon footprint, therefore reduce the release of CO2 into the atmosphere. And of course, this is a key and pressing industry goal, which is to reach net zero by 2050, not so long into the future. And of course, an aspect of this is to allow more existing structures to be retained in beneficial use. So let's look at one of the primary concerns which are influencing today's society: global temperature changes in recent decades. In the NOAA 2020 annual Global Climate Change Report, this presents information about global temperature changes between 1884 and 2020. So here on the left, you can see a graphic of the global temperature situation in 1884, and here on the right, the one for 2019. You can see that the 1884 graphic presents in blue hues, which represent a temperature lower than the mean for the 20th century, and brown here, yellow, which represents an increase above the average for the 20th century. So, the 10 globally warmest years since 1884 have occurred since 2005. 2016 was the highest, 2020 was the second highest, and 2019 was the third highest. And all of these are about 1 degree C above the global average, the average global land and ocean surface temperature over the 3 decades, 1951 to 1980. But a manifestation of these higher temperatures is a greater number of climate impacts and disasters, and the information presented here comes from the United Nations Office for Disaster Risk Reduction. You'll see that the data is compiled in terms of 2 study periods, 1980 to 1999 and 2000 to 2019, i.e. 2 periods of 20 years. In the latter study period, there's been an increase of 74% in the number of reported disasters, a 24% increase in the number of people affected to 4 billion, and economic losses have risen by 82% to almost $3 trillion in this 2-decade period. It's also informative to look at the total disaster events by type over these 2 study periods. And you can see a dramatic increase in the number of flood incidents, up by 134%, and the total number of storms, up by 40% over that timescale. And what is clear from these data is that the number of disasters is increasing, their severity is growing in intensity, and this correlates with an increasing Earth temperature and higher levels of CO2 in the atmosphere. So how can construction reduce its embodied carbon footprint and release less CO2 into the atmosphere? So the graphic on the left here shows the life cycle of a project from planning, design, build and operate on the horizontal axis, and on the vertical axis, the CO2 reduction potential within a project. So here at the top, 100%, there's the possibility of building nothing or as little as possible. So that would be the most effective strategy, but not perhaps particularly helpful. A more useful approach, which achieves a good reduction in the carbon footprint, is to repurpose or renovate existing buildings rather than demolishing and building anew. And there's an interesting case study undertaken for the renovation of the United Nations New York City headquarters campus. And this looked at the carbon saving benefits of retrofitting and renovation versus demolition and new build, i.e. the goal was to try and find out which approach is best. So this made a comparative study of both embodied and operational carbon used by the buildings. And it was estimated it would take 35 to 70 years to offset the initial outlays of embodied carbon required if the UN campus were demolished and reconstructed, taking into account the operational efficiencies which would have been gained from the benefits of new construction. So the study shows a strong case for retrofits and renovations of existing building stock rather than demolition and new build. In terms of adaptation of existing assets, I've got 2 examples of the conversion of grain silos into new uses. On the first look at this, you would think that the conversion of a grain silo wasn't a particularly good prospect, but engineers and people are innovative, and this slide here illustrates the conversion of a grain silo in the port of Oslo into student housing. And then I have a second example taken from the adaptation of the grain silos in the port of Cape Town in South Africa, where the existing structure was converted into 2 uses, one as the Zeitz Museum of Contemporary Art of Africa, the Mocha, shown here, and a 5-star hotel called the Silo. So you can see the existing concrete structure, which was adapted and modified quite extensively, and elements of new build introduced above to complete the scheme. This, of course, brings us to reflect upon the conceptual scope of Model Code 2020 that deals with both new, existing, altered and adapted, as well as retrofitted concrete structures. And as you might expect, this links to the adoption of a performance-based approach, which is required to facilitate the usage of new and evolving materials and technologies, as well as to gain greater material and structural efficiencies. Let me just explain some of the process steps which we consider will be relevant to sustainable design. We start with the performance requirements defined by the social aspects, environmental aspects and economic aspects. And these are taken together, and the goal is to enable a process which facilitates the selection of structural design and assessment parameters so applicable to new as well as existing structures. We have various tools and techniques which help us do this. Conceptual design, linking across the requirements defined by the 3 pillars, and of course aspects such as the life cycle management philosophy and tactics to be employed for the new or adapted existing structure throughout its life. The goal of these considerations is to develop candidate schemes and scenarios to meet the objectives of the new project. And of course, this is done through an iterative process, and we're familiar with that in our current design procedures. And the goal here, of course, is to select the best candidate scheme or scenarios for further consideration. This would involve the verification of social performance, environmental performance, and economic performance. And of course, as engineers, we know social performance better in terms of the parameters which are defined to establish structural performance in our contemporary work. Of course, what this does is lead forward to a sustainable decision-making process, which would be used to establish the most suitable scenario candidate scheme for detailed development, very much in the way we currently work. But of course, our considerations currently are limited to cost aspects. Let us now look at the Model Code 2020 table of contents and start by considering the evolution of the FIB Model Code for structural concrete. There have been 4 editions, 1970, 1978, 1990, and 2010. And the evolution of these codes have influenced the development, amongst others, of the CEN Eurocode 2 for concrete structures. It's also impacted upon the development of the Asian and African model codes. And our current version, Model Code 2020, will for the first time include significant provisions for existing concrete structures. Our starting point, of course, was the existing code, Model Code 2010, which was published in whole back in 2013. And that contained 5 parts, 10 chapters, and about 400 pages. Model Code 2020, with its greatly extended technical scope and coverage, will be larger. It addresses new build, as does Model Code 2010, but also goes on to deal with existing concrete structures and the technical developments which have occurred since Model Code 2010 was published. So Model Code 2020 is envisaged to have 10 parts, 39 chapters, and a page count in the order of 700 to 800 pages. The code will be supported by additional FIB bulletins, which will provide supplementary information, and these will be used to reduce the page count and the technical content in the code. Just taking the parts and chapters in the table of content. Part 1 deals with scope and terminology. Part 2 deals with basic principles. And in chapters 3 to 10, this outlines the sustainability perspective to be adopted, the performance-based approach, principles of life cycle management, structural design and assessment, execution, conservation, and matters relating to circularity and dismantlement, as well as principles of quality and information management. Part 3 deals with principles of structural verification, setting out an evaluation framework and the principles to be applied for structural design and assessment. Part 4 deals with actions on structure. So this is a completely new part to the code, providing information for, amongst others, probabilistic analysis of verification of performance. Part 5 deals with input data for materials. In chapters 14 to 19, this deals with concretes, a whole family of concretes, of course, reinforcing steel and pre-stressing systems, non-metallic reinforcement, as well as fibre reinforced concrete and ultra-high performance concrete. And chapter 19, which deals with protected materials and systems, is of course a new section as it deals with the requirements for existing structures. Part 6 deals with input data for interfaces. As we have more materials, we will have more interfaces. So chapters 20 to 25 concern with the bond of embedded steel reinforcement, non-metallic reinforcement, as well as externally applied reinforcements. Chapter 23 deals with concrete to concrete, so that's new concrete applied to old concrete. And 24 is a new section concerned with concrete to steel sections involving mechanical interlocks, studs, etc. And 25 deals with anchorages in concrete. Part 7, design and assessment procedures, is the main technical content of the code. This is the core of the work. Chapters 26 to 34 deal with all of those different aspects and follow through the design and life cycle of a structure. So we have conceptual approach to design and assessment, approach to design, approach to assessment, structural analysis and dimensioning procedures, and then a very major component of this chapter and the entire code are the verification procedures for structural performance, safety and related matters, and then their evaluation of other aspects of social performance, such as serviceability, durability and the like. 32 is concerned with environmental quality. That's dealt with by life cycle analysis and evaluation of economic efficiency in 33. That's addressed by life cycle costing. And then the chapter 34 deals with sustainable decision making, which I've referred to before. Part 8 deals with execution, its management of both constructed works and the execution of interventions upon existing structures. And again, that's a new section. In terms of the latter parts of the code, we've got part 9 deals with conservation. In other terms, that's life cycle management of an existing structure, both treated in design and of course, as an existing structure. And part 10 deals with circularity, dismantlement and reuse. I mentioned that there's an associated program of preparing supporting FIB bulletins. This draws upon the background work of commissions, task groups and Model Code 2020 action groups. So it's supplementary information. And one of the benefits of this project is that many of these bulletins are being developed as the Model Code 2020 work progresses rather than afterwards. In terms of the target timetable for the development of Model Code 2020 and making a draft text available for public review. The first goal is to obtain the author drafts of all the different sections, and we hope to have these received by mid-2021 or certainly by the autumn of this year. And then that leads into a harmonization process led by an editorial group with its goal of producing an FIB bulletin of the draft Model Code 2020, which would be available for public review and comment, and hopefully we'd have that done by the end of 2021 or early 2022. Let me now move on to the sustainability and the performance-based approaches, which I've mentioned earlier. These are applicable to the design and construction and life cycle management of both new concrete structures, as well as the adaptation, upgrading, repair, life extension, etc., of existing concrete structures. Now, it's worth reflecting upon what the performance-based approach is. So it's in practice, it's the thinking and working in terms of the end goals rather than the means by which the objective should be achieved. It's concerned with what a building, material or product or complete building is required to do, i.e. its performance, and not with prescribing how it is to be formulated or constructed. It applies to materials, products, methods, as well as parts of structures, internal structures, and it can also be applied to services and processes. It's not new. I think it was first applied in France by CSTB in the 1950s. And just to give an illustrative example, if one considers a 4-tier approach of linked and overlapping performance or outcomes-based requirements, specifications or testing regimes, tier 1, the upper one, would be addressing the owners, users or stakeholders' higher level performance or outcome-based requirements. So these are likely to be related to the social performance requirements for the structure or the constructed asset. Tier 2 is concerned with turning the Tier 1 requirements into technical strategies, technical performance requirements with associated metrics, so that the performance of the structure, the safety of the structure, its stiffness, its resilience, etc., can be evaluated. Contractors and other constructors would be, in this example, seen as dealing with the Tier 3 procedures, which would be creating appropriate performance-based specifications to select and procure suitable materials and manufacturing systems to address the requirements set down in Tier 2. And then at Tier 4, material suppliers and manufacturers would again need appropriate performance-based specifications to provide suitable materials and manufactured systems to achieve the requirements set down in Tier 3. So all of these processes need appropriate metrics so that their performance or success can be judged and an appropriate degree of reliability established. I had hoped to be able to give you an illustrative example of a Tier 1 performance requirements and that conversion into an indicative Tier 2 engineering technical performance requirements, but it takes too long for the period I've been allocated today. But there is a paper which was given at the FIB Symposium 2021 in Lisbon in June. That's referenced in the written paper, so I'll just leave you with that at the moment. Just to bring this illustration of the Tier 2 engineering performance requirements to a close, just like to indicate that obviously there are significant challenges in achieving this, but the challenges tend to come in terms of defining the technical parameters. So how precisely can they be defined? What performance metrics and tests might be used effectively to monitor progress towards the desired goals? But also it's important to recognise that you need to have commercial and contractual parameters included in this, because there's other aspects in terms of contractual relationships, information flows, responsibilities, the amount of payment received, the risks to be considered, and who carries those within the team. I give you two illustrative references, one by the American Concrete Institute, their report 329, that deals with technical and commercial aspects, and then a paper by Den and Herman on the performance-based approach for mechanical concrete properties, and that one is technical in nature. So let's move on and talk a little bit about some of the innovations incorporated in Model Code 2020. Let's start with improved materials and mechanical models. Of course, these are very important for existing structures. And looking at this in regard to seeking models that would be better at giving the actual capacity of an existing structure. The approach is based upon performance design. So it looks at the ability of the structure to fulfill the performance requirements for the design service life at the required probability level. Of course, limit state concepts are used, ultimate limit state, serviceability limit states, condition limit states, and so on. And of course, with the existing structures, you have to incorporate deterioration effects which might reduce the structural resistance, and that's shown by the blue line here. And of course, it may be that there's an increasing load effect with time. So this may be actual physical load increasing with time, or it might be environmental loads affecting durability. So on the horizontal axis here, we have time, and on the vertical axis, we have structural performance and related parameters. So we have probability distributions for the loading and probability distributions for the resistance shown here, and of course they overlap increasingly with time, but there may well be in terms of structural behaviors resistances which are not typically taken into account in design, such as compressive membrane action in deck slabs. So that gives a basis for justifying a larger structural resistance. And of course, that gives a basis for justifying extended service life. In terms of technical objectives of model code, there is a desire to facilitate the wider use of levels of approximation approach, or levels of refinement, as it's sometimes referred to. So what this is in simple terms is shown on this graphic here. So on the horizontal axis, we've got the effort involved in analysis, and here the accuracy. So level 1 and level 2 represent a simple, conservative structural or material model, and here at level 4, a more advanced, more accurate model, perhaps in this instance a nonlinear finite element model. And what we're expecting is improved accuracy of the prediction in terms of say, the strength, and at the lower levels of approximation, a smaller analysis effort, but a more conservative result being given. Let's look at an application of this concept in terms of justifying a higher load capacity in an existing concrete structure using compressive membrane action and levels of approximation calculations. So here we have compressive membrane action developing in a deck slab by virtue of arching. Relationship can be developed between the rotation angle and the punching shear capacity. And if we portray that as shown in this graphic here, a relationship between rotation and punching shear load, we have different considerations in terms of the technical models. No pre-stressing applied, pre-stressing in an elemental level of approximation, so say level 1, pre-stressing with compressive membrane action, and also an advanced level of approximation, so potentially nonlinear finite elements. And that gives us these 3 different levels of approximation estimates of the strength. These approaches can also be applied to the more general application of structural assessment of existing structures. This example is taken from the SAMCO project report in 2006. It defines 6 levels of approximation, level 0, A0 through to A5, and it recognizes aspects such as whether it's a qualitative assessment or a quantitative assessment, and whether it's measurement-based assessment or a model-based assessment, and you end up with a significant range of approaches for estimating the strength of the structure. In terms of modelling of deterioration processes, Model Code 2020 seeks to incorporate the initiation as well as the propagation of deterioration, or models for that. So that's in terms of deterioration of the concrete, but also in terms of reinforcement corrosion. So these approaches involve both material models and structural models. Okay. Just thinking in terms of life cycle management of an existing structure, there's a role to be played by monitoring and in terms of the value of information gathered. So the objectives of this approach, these techniques, are to improve the quality and safety of the constructed assets being considered, generally to extend their useful service life, provide diagnostics and assist infrastructure risk assessment and management, potentially to monitor safety in real time, and I think that's more of a future aspiration. And of course, these facilities provide better tools to the engineering community. And again, there's another reference here to a paper given at the ICC RRR 2018 conference in Cape Town in November 2018. Again, that's given in the references to the paper. I'd also draw attention, but I can't really say anything because I'd have to say lots about the innovations relating to undertaking interventions upon structures. And I cite two references here, a conference in Lisbon in November 2018, and also the paper given at the FIB symposium this year, also in Lisbon, and they provide quite a lot of information as to the developments incorporated in the code. So this brings me to my concluding comments. In terms of Model Code 2020, our goals and outcomes will include improved technical guidance for the design of new structures, as well as the assessment, adaptation, conservation of existing structures. So these capabilities should provide better tools to undertake assessment and interventions upon deteriorating structures, to either upgrade them or extend their useful performance lives. So summarising, it's hoped that Model Code 2020 intervention and improvements can assist in the creation of durable low carbon structures, both new, adapted and upgraded. And as I say, provide better tools and techniques for the design of new structures and then also dealing with the existing structures. But essentially the goal is to have a new version of the Model Code Model Code for concrete structures, which is better suited to future demands and the circumstances to be encountered in future years. Thank you for your attention, and I'll be ready to answer any queries, but I just have one final postscript, a thought for you. I've talked about the 3 pillars, and these have a long history. Today, we've talked about 3 pillars of sustainability, social, economic, and environmental. So that deals with safety, functional resilience, and other performance requirements. So safety, serviceability, aesthetics, etc. Life cycle costs and benefits, life cycle environmental impacts and benefits. But previously, the Romans had a similar system where they were seeking balance by considering 3 pillars: firmitas, utilitas, and then venustas. So firmness and strength, utility, functionality, and beauty, which again we would now refer back to as safety, serviceability, and aesthetics. But very interestingly, these matters were being discussed by Vitruvius, a Roman writer, architect, and engineer, who wrote about these matters some 2,000 years ago. So we have a long history, a long path of trying to find the appropriate balance for society's considerations. Thank you very much.